All right, let's take a look at exponential functions in section 4.1. The exponential function f with base b is f of x equals b to the x. B is a positive constant other than 1, b is bigger than 0, and b is not equal to 1. X can be any real number. Here are some characteristics of exponential functions. If b is bigger than 1, the function is increasing, rising from left to right. If b is between 0 and 1, the function is decreasing, falling from left to right. Both cases have 0, 1 as the y-intercept. Both cases have the x-axis as a horizontal asymptote. But notice if b is bigger than 1, the horizontal asymptote is on the left end. If b is between 0 and 1, the horizontal asymptote, the x-axis, is on the right end. Let's take a look at graphing f of x equals 3 to the x and g of x equals 1/3 to the x. So we're going to make a table of coordinates. So we're going to pick our x, and then we know the function value is our y value. So I'm going to pick x equal -2. 3 to the -2 is 1 over 3 squared, and that's 1 over 9. 1/3 to the -2 is 3 squared, which is 9. So when I apply a negative exponent to a fraction, I can invert the fraction and change the sign of the exponent. So when x is -1, 3 to the -1 is 1 over 3 to the first, which is 1/3. 1/3 to the -1 is 3 to the first. Invert the fraction, change the sign of the exponent. 3 to the 0 is 1, and so is 1/3 to the 0. 3 to the first is 3. 1/3 to the first is 1/3. 3 squared is 9. 1/3 squared is 1/3 times 1/3, which equals 1/9. So I am going to make the graph of f of x equals 3 to the x blue, and I'm going to make the graph of g of x equals 1/3 to the x red. So I'm going to plot the 5 points for each graph. So when x is -2, f is 1/9, so y is 1/9. When x is -1, y is 1/3 for f. When x is 0, y is 1 for f. When x is 1, y is 3. When x is 2, y is 9 for the function f, which I'm sketching in blue. All right, it's hard for me to draw this curve as smoothly as it should be drawn, but I did the best I could with my electronic tablet. When x is -2, y is 9 for g. When x is -1, y is 3. When x is 0, y is 1. When x is 1, y is 1/3. When x is 2, y is 1/9 for g. And I sketched that decreasing functions graph in red. So remember, if b is between 0 and 1, the graph is decreasing. So we see a falling graph for g because the base b is between 0 and 1. Now for f, which is the blue graph, b is bigger than 1. My base is 3, so the graph was increasing. Let's look at using Mathematica to actually graph these functions. So I'm going to go to Start, All Programs, Wolfram Mathematica, and select Mathematica 10.1. a new document, a notebook, and I'm going to increase the magnification to 200%. And I'm going to use my plot function. I'm going to use the second set of instructions, which allow me to give more than one function. And they have to be given as a set. So those two functions are separated by a comma and enclosed in a set of braces. I'm going to let x go from -2 to 2. And I'm going to give my plot range. And notice that I get an error message because I actually got ahead of myself and didn't give the plot range. I actually gave what I wanted to give for plot style. So I'm going to fix that. So let's get rid of this error message. So basically it didn't know what I was talking about. So I'm going to go in and I'm going to actually give it the plot range. I'm going to go from -2 to 10 with my y values. So the plot range is the range of y values. So I'm going to go from -2, that's going to be my smallest y, to 10. And then plot style, notice I have a set that contains two sets. The first set tells me about F, which I want to be blue and thick. The second set tells me about G, which I want to be red and thick. So that's the plot style information. I went to graphics, drawing tools, and I'm going to put arrows on these two graphs. So I'm going to strokes and change the color. And I'm going to select the arrow tool, and I'm going to put an arrow on the tip of F. There it is. I'll kind of move that in place, and I'll put an arrow at the lower end of the graph also. Alright, so I'm also going to do that for G. Put red arrow at each end. Change the color to red. Select the arrow tool. Oops, and it changed back to blue. I'll change that to red. And I'll also put the arrow on the bottom of G's graph. And just as we knew, these are nice smooth curves. And notice how much better those look than my drawing. Let's look at solving applications involving exponential functions. E. coli bacteria reproduce by simple cell division, known as binary fission. Under ideal conditions, a population of E. coli bacteria can double every 20 minutes. So we're going to model this with n of t equals n0, the initial count or number of bacteria, and we want to let it be 5, and we want to find how many bacteria will there be in 3 hours. So let's use Mathematica to do this. I want to point out a problem we run into in Mathematica. Okay, so we're going to put in the values of the function, and notice that looking more carefully at the function, we see time has to be in minutes. So 3 hours is 180 minutes. Every hour has 60 minutes in it. So we replace t with 180. And we use Mathematica to do our calculation. and we get 2,560. And this is actually an exact value, not an approximation. All right, so let's so basically we see there are 2,560 bacteria after 3 hours. And whenever we use a function, we have to pay careful attention to what the variables represent. Notice t represents minutes, so we have to convert 3 hours into minutes in order to use the formula properly. Otherwise, we would have had misinformation. So let's start with 8 bacteria, and let's see what happens in 3 hours. How many bacteria are present in 3 hours or 180 minutes? So we want to calculate, and notice we're actually calculating, in part A we were calculating n of 180, since the function is defined in terms of minutes. Here we're also calculating n of 180, but our starting or initial value of or number of bacteria is 8 instead of 5. And we want to see what happens. Remember, these are exact values we're getting back in this particular case, since our exponent actually turns into an integer. Alright, so we control copy and then control paste it and just change that 5 to an 8, and we got 4,096 as the number of bacteria after 3 hours when we start with 8 E. coli bacteria in the culture. So that is rapid growth. That's why you can get so sick if the culture is within you. Alright, let's start with 8 bacteria, but this time let's see what happens in 10 hours, which is 600 minutes. So let's find n of 600. 8 times 2 to the 0.5 times 600. So I'm going to use Mathematica to do this calculation, and you can imagine this is going to be really huge, a really huge number. And notice I'm in the billions of bacteria now, just by letting time increase to 10 hours. So 7 additional hours takes me into millions of bacteria. So this is approximately 9 times 10 to the 9th. So there are about 9 billion bacteria in 10 hours. So that is what makes you so sick when this invades your system. Let's look at one last application where we are looking at our periodic compound interest formula. So this is an example of a function that is an exponential function. P is my original investment, R is my interest rate, N is how many times the interest is compounded per year, and A is the amount accumulated, or the total amount after T years. So we want to find out which yields the greater return. Investing $5,000 at 7.35%, where the compounding occurs daily, or investing $5,000 at a higher percentage of 7.4%, compounding quarterly. So when we compound daily, that's 365 times a year. So we replace N with 365, T with 10, R with 0.0735, and P with 5,000. To find the other value, the only difference is our N is 4, quarterly compounding is 4 times a year, and our R is 0.074. Now we're going to run into a problem when we use Mathematica here, and I want to kind of show you what that problem is. So I'm going to plug this in. Let me fit this onto the screen so that we can see what I've written and what I'm entering in. So notice how I'm very easily able to enter this in. Notice for any type of calculating device that allows you to just enter this straight in, notice that that exponent needs to be, that product in the exponential position needs to be parenthesized in order to get correct results. Alright, so Mathematica gives me this to the nearest tenth, not to the nearest hundredth. Whenever you're dealing with money, you want to round to the nearest hundredth if there is cent, if you don't have whole dollars. So notice for the 7.35% compounded daily, I get, using Mathematica, I get $10,426.60. 7.4% compounded quarterly, Mathematica calculation is $10,409.10. And even if I go in and I try to use my numerical function and tell it to give me 8 significant digits, it still doesn't improve that result. I still just get to the nearest tenth. So the nature of the functions are such that it's not actually giving me, if you were doing my MATLAB problem and you put in these results, the answer would be incorrect. So it's better to use a calculator, and I want to show you how the result changes when I do use my calculator. Instead of getting 60 cents, I get 64 cents. Instead of getting 10 cents on the second calculation, I actually get 6 cents. And that could be the difference between getting that calculation right or wrong. So you do have to be a little bit careful. It turns out, though, the investment at 7.35% compounded daily yields the greater return. Of $10,426.64. So compounding more frequently is actually more powerful than a higher interest rate with significantly less compoundings. So you're compounding 90 times more frequently.